In this module, I'm going to tell you about partial melting of the mantle to generate basaltic magmas, something that we've begun to discuss, and about magmatic differentiation. Here's a model mid-ocean ridge where the crustal rocks, that's this pile of rocks here, the sediments on the base on the seafloor, the basalts, and the gabbros at the base of the crust, the oceanic crust. This is spreading, and so the crust is being stretched thin and fractured, and this allows the mantle down here to upwell and into the space that's created beneath the thinning crust. And what happens is we get a partial melt of the mantle forming because the pressure is reduced on the mantle. And the partial melts are basaltic. And those are the basalts that are then erupted onto the surface of the seafloor and form the oceanic crust. I've also talked to you about melts that are generated in a volcanic arc, and here's an island arc as an example, where the subducting oceanic crust is metamorphosed, and those hydrous minerals, the phyllosilicates and the amphiboles, are metamorphosed to form feldspars and pyroxenes instead of the amphiboles. That structural water is released into the mantle wedge that's above the subducting slab, and that lowers the melting temperature of the mantle itself. And so partial melts of the mantle are formed, and those are also basaltic. And that's what rises buoyantly and is intruded into the crust of the arc or the edge of the continent, whatever the case may be. Now, in the case of an island arc, we aren't ending up necessarily with basalts that are erupted or that form the rocks of the crust. There's a process of differentiation, and that's marked on here, that whereby we're taking those basalts and doing something, either physical or chemical processes that change the composition of the magmas that are in the continental crust, because the overall composition of these volcanic arcs is andesitic or granodiorite, not basalt. There are, as far as melting the mantle, there are basically 3 different ways that you can partially melt the mantle to generate basaltic melts. You can increase the temperature of the mantle. That is essentially what's happening at the core mantle boundary, where the hotspot plumes are forming and then rising up through the mantle and then erupting at those hotspots on the surface of the crust, whether it's continental crust or oceanic crust. You can decrease the pressure, and this is the decompression melting that I mentioned at the mid-ocean ridges, or the same process that happens on continental rifts, where you're thinning the crust, reducing the pressure on the mantle, and then partially melting it. Or you can add fluids. And this is what I'm talking about when I say that you're lowering the melting temperature of the mantle, that's the mantle wedge that's above the subducting slab at a volcanic arc or continental arc, any subduction zone. Now, this diagram over on the left shows you several things. It shows you pressure on the left-hand side, the corresponding depth on the right, and then temperature across the top. This geotherm that's depicted here, this line, that is representing the temperature of the mantle, the peridotite, as you go down in depth through the mantle. So at 50 kilometers depth, the temperature of the mantle should be about, it looks like about 1100 degrees Celsius. And we also see this dashed white line here that is the dry melting curve of the peridotite. What that means is if there's no water involved, that a dry piece of mantle is going to start melting at those pressures and corresponding depths. So if we go back to 50 kilometers here, on that melting curve, that's showing us, let's see, 50 kilometers, that's showing us that the mantle would have to be something like 13 to 1400 degrees Celsius in order to melt at that depth. But we know that the mantle's not that hot. It's only about 1100 degrees Celsius, and so it's solid. Now, if you add some water to the mantle, as you do in a subduction zone, that melting curve for the peridotite changes. And that's what this line is here. This is the wet mantle melting curve, essentially. And what that's showing us is that where that wet melting curve intersects the geotherm, that's the temperature and depth at which we can get melt. And so what this means is that starting at about 40 something, somewhere about 45 kilometers deep, mantle rocks become hot enough to melt. And so everything right of this wet melting curve, everything on this side is melt plus solid mantle, solid peridotite. So this is what I mean by partial melting, that you're starting to melt as soon as the wet melting curve intersects the geotherm, right here, and you start to melt the mantle. Now this is what I'm talking about when I'm saying in a subduction zone, those structural fluids that are released from the subducting oceanic crust as it's being metamorphosed enter the mantle wedge above the subducting crust and then reduce the melting temperature from this dry melting curve to the wet melting curve. That's the reduction I'm talking about, and that's what's allowing the mantle to melt. Now, as far as decompression melting at a mid-ocean ridge or at a continental rift zone, we've discussed this geotherm for the mantle. Imagine if you remove the overlying crust above the mantle, what you're essentially doing is moving this curve up higher. So we're just shifting it to shallower depths. And the effect of that is that the geotherm is going to intersect either wet or dry mantle at a lower temperature and near to the surface of the earth. So that's essentially all you're doing is shifting that geotherm and intersecting what's probably the dry melting curve. You're intersecting that at a much lower temperature and shallow depths. That's the effect of decompressing the mantle by thinning that overlying oceanic or continental crust. I don't think I need to explain increasing temperature in order to melt the mantle. That's pretty straightforward, I think, to everybody. And the heat there is coming from the core, and it's heating the mantle up enough to partially melt the lower parts of the mantle, and that's what's rising up in the hot spots. All right, so we start with basalt melts. Those are the partial melts of the mantle that we're starting with at mid-ocean ridges and in subduction zones. But that's not what forms the continents. So we're going to have to do something to those melts, those magmas, in order to change the chemistry to produce what's dominantly like an andesitic or a granodiorite magma that comprises the continental volcanic arcs and the continents. And how we do that is this process of magmatic differentiation. And that's any process by which the magma is able to diversify and produces a magma or rock of different composition. And so in this diagram, it's just cartoons showing different ways that you might do this. And I'll show you some examples in real rocks. But you can imagine an initial basalt magma entering the crust, and it could mix with another magma. You could have early forming crystals crystallizing and settling out by gravity onto the magma chamber floor, and that changes the chemistry of the remaining melt. You could also incorporate or assimilate pieces of the surrounding continental crust into the magma and change its chemistry. So there are a number of different ways that we can do this. I've been talking about partial melts of the mantle. You can also have partial melts of the basalts after they enter the crust, or a partial melt of a granodiorite to produce a leucogranite. And all that I'm saying by partial melting is that you're separating a partially melted rock from the solid that's left behind. And so in this example here, I've got Magmatite. These sweaty rocks that they're just getting hot enough, they're starting to melt. And if you accumulate enough of this melt in these white little leucosomes here, if you accumulate enough, then you can separate that melt from the remaining body. So here's an example of a granitic looking dike in a rock that looks much different than what's left behind. And so if you have enough melt of accumulated, so they can move, it can go off in dikes and separate away from the rock that generated it, you're removing those minerals and those elements from the rock. You're removing some silica, you're removing the sodium, the potassium, the aluminum, and you're leaving behind something that is a changed chemistry. And that's what I mean by partial melting, and how you change the chemistry by removing those minerals. And the minerals that are going to make up those leucogranite dikes are going to be the minerals that melt at the lowest temperatures. So those minerals in the bottom of Bowen's reaction series, the quartz, the K-spar, the muscovite, the sodium-bearing plagioclase. You can also fractionate the melt, and this is what I mean by taking those early forming crystals in a magma. So these are the minerals that are at the top of Bowen's reaction series. So these are more likely to be, in this example, more likely to be olivines or pyroxenes that crystallize in a melt and then fall to the magma chamber floor. And this is a layered cumulate. And so these are crystals that have settled because of gravity. It's very slowly, but they settle and fall to the magma chamber floor. And what they leave behind is a change. The chemistry of the magma they leave behind is changed, right? You take out some of the magnesium and the iron and the calcium, you separate it out in the crystal. That leaves the magma less rich in the calcium, sodium, or calcium, iron, and magnesium. You can mix magmas, and so the result would be, I have a picture in a moment, but the result would be a chemistry that is a mixture between a rhyolite with a lot of silica and maybe a basalt. It depends on which two magmas you're mixing, but you would see a chemical change that would span those two rock types. And this is the Harker diagram that this caption is referring to. It's simply those major elements plotted against silica to characterize a rock. And so in a magma, when you're mixing magma, you're seeing a range of chemistries between two end members. Here's an example of magma mixing where you clearly have two different phases. You've got a darker rock, you have a lighter rock mixing. It's crystallized now, but it's clear that there were two compositions there mixing together. Here's another example over here of what are pillow basalts at the bottom of a granitic magma chamber. So these dark blobs are the pillow basalts, and the lighter colored rock in here, that's the granite that's now crystallized. So you do get instances where you can mix and mingle magmas to change their chemistry. You can assimilate pieces of the crust that's surrounding a magma chamber. So we're incorporating xenoliths, these foreign rocks that aren't part of the magma body itself. They're breaking off of the surrounding rock, dropping down into an intrusion. And it's clear here you're seeing this light colored, what looks like a granite, versus this darker, we'll call that an andesite. And those can start to melt and actually change the chemistry of the magma that they've fallen into. All right, so when we're changing the chemistry of these magmas during the process of whatever combination or single process of magmatic differentiation we're undergoing, the result is that we're going to change the chemistry over time. It's going to go from more magnesium compositions to more potassium and sodium rich compositions. Depending on the rock, it's going to take maybe a different path. It may go from magnesium to iron, and then iron rich, and then toward the alkalis. But the upshot is you're going to change from the initial basalt partial melt in whatever tectonic setting you're in, and you're going to move towards something that's much more like rhyolite over time. And what you learned in this segment was that partial melting of the mantle to generate basaltic melts happens at mid-ocean ridges and continental rifts by decompression melting. At subduction zones, it's happening where you're lowering the melting temperature of the mantle by adding water. At hot spots, that is heat that's coming from the core mantle boundary to heat the mantle and generate the basaltic melts that are partial melts of the mantle. And then we talked about magmatic differentiation, and we discussed a few different ways that you could differentiate those early partial melts by partially melting a melt, again, by crystal fractionation. That is, those early forming crystals are dropping out, settling out of a magma and changing the chemistry of the magma that's left behind. You can mix or mingle magmas to change the chemistry. And you can assimilate rocks, xenoliths, from wall rock around the magma and melt those pieces or crystals that are coming from the country rock and change the chemistry of the magma itself.